David Can here with another question from the IB question bank in topic 11.1. We're looking at electromagnetic induction. We have a small coil placed with its plane parallel to a long, straight, current-carrying wire as shown below. The first part is just to state Faraday's law of electromagnetic induction, which is a thing that we have an equation for. E equals negative delta phi on delta t, where E is the induced EMF, delta phi is the change in flux, and delta t is a period of time. Anytime you have an equation for the thing you're trying to state or define, it's a good idea to put the equation in and define all the terms. Often you can get full credit for that. Sometimes you can't, though, so you should also try to describe what you're trying to say in words. So Faraday's law of induction tells us that EMF induced in a circuit, or EMF induced in a wire, is proportional to the change in, let's bring that over here, proportional to the change in flux with time experienced by that wire. So the faster the flux changes, the higher the EMF. We'll use the law to explain why, when the current in the wire changes, an EMF is induced in the coil. Well, the current generates a magnetic field, and thus a flux in the coil. So current generates magnetic fields, and flux is proportional to that magnetic field. So changing the current, therefore changing the current changes the magnetic field strength, and thus a changing magnetic field, a changing flux with time is created. Producing an EMF. That sounds pretty good. Next up, we're given some diagrams. We have the current in the wire with time, and blank graphs for magnetic flux with time and EMF with time. And we're asked to draw on the axes a graph of the magnetic flux in the coil and the EMF in the coil. So we said that the current generates a magnetic field, and the magnetic field is proportional to the flux. So the current is proportional to the magnetic field strength, which is proportional to the flux. So these two graphs should wind up being basically the same. Whenever the current is high, the magnetic field strength will be high and the flux will be high. Whenever it's low, low, low. Whenever it's high, 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 low, low, low. And whenever the current is zero, we get no magnetic field strength and therefore no flux. So we wind up with basically a copy of the same graph. We'll try and draw a neat sinusoid. Neat as we can. And that's fine. We don't need to worry about the amplitude of the sinusoid because there's no units on the y-axis. So the amplitude could represent any value, whatever it needs to represent. Next up is the EMF. We know from Faraday's law that the EMF is the negative change in flux with time. So what we're going to do is we're going to look at the graph of the flux and look for where it's changing and where it's not changing. I'll tell you it's not changing here, 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 and here. The slope of the graph with time is 0. So there's no change. That means that the EMF is 0. 0, 0, and 0. So where is there an EMF? Where is the flux changing? It is changing here, 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 and here. Here we see the flux rising, and the flux falling, and the flux rising, and the flux falling, and the flux rising. We just have to remember this negative sign, which tells us that the value of the EMF is the opposite of what the change in flux with time is doing. So whenever the flux is rising at its maximum rate, the EMF is at a minimum. And whenever the flux is falling at its maximum rate, the EMF is at a maximum. And we get another sinusoid, but it is not the same sinusoid. It's out of phase by 90 degrees. Try and draw a nice, neat sinusoid. Out of phase by 90 degrees. Next up, we want to state and explain the effect of the maximum EMF induced in the coil when the coil is further away from the wire. So when we move the coil further from the wire, what happens to the EMF induced in the coil? Further from the wire, the range of flux is smaller. Basically, further away from the wire, the magnetic field strength is weaker, so the flux is smaller. But the period of the flux is the same. It doesn't affect the period of the wave. It just becomes shorter. The wave becomes shorter. It's squished vertically. What this means is that less change in flux occurs. The flux has to go through a smaller change in the same amount of time. And so a smaller maximum EMF is generated. Lastly, we're told that such a coil may be used to measure large alternating currents in high voltage cables. So the idea here is that you have some current here, it's high, it's dangerous, we don't want to touch it. So we can measure it using this coil. The more current, the more magnetic field. The more magnetic field, the higher the flux. And the more the flux changes, the bigger the extremes in the flux, the more EMF we generate. So by looking at the EMF generated in this coil, we can get an indication of the current in this wire. What are the advantages of measuring current in this way? Well, one advantage is it's safer. You don't need to make contact with the dangerous cable. But it does have a disadvantage, and the disadvantage is that the measurement is limited in precision by the precision with which you can place the measurement loop, with the precision with which you can place the coil. What I'm trying to say here is that because the magnetic field strength will vary depending on how far away the coil is from the wire, we determined that that will affect the EMF induced in the coil. But the EMF is the only thing that you're using to judge the current in the wire. So you can't tell the difference between the EMF varying because the current is varying and the EMF varying because the position of the coil is varying. So you can't be more precise than how precisely you can hold that coil in place.